So in this section, we'll implement cosine and sine functions as Taylor series expansion. I have imported some libraries, in particular this last one for facilitating the animation. And I will show the animation in the Jupyter notebook itself. So this is the magic command for that. Before we build the Taylor series expansion, let's build the building blocks of Taylor series and take advantage of all the properties that we saw in the PowerPoint slides. So firstly, let's create an index for the series. Let's say an index I, which is going from 0 to say, let's say 10 in steps of 1. So how does this look? So here we are. So this is just the index of the series, and we are going to leverage on the properties that there are even series, there are odd series, and there are alternating signs. So we have to figure a way out how to go about implementing it using this index that we have created here. So let me just write it down, print it out properly. The index of the series, which is equal to this index of the series. So now using this series index, we want to create even numbers. So how we can do it is we can take this and multiply this index by 2. And when we do this, we will get even numbers. So here we are then. Let's call it even series, and this is even. So let me just, so here you are, and just a minute. So there we are. These are all from this index, which is 0, 1, 2, 3, 4, 5. We have extracted the even numbers, and similarly we can extract the odd numbers by adding 1 to the previous series, which is, if we do this, if we add 1 to the even series, we get odd numbers. So in this way we can generate the odd numbers. So let me just call it odd series, and let me just print it. So here we are then. So these are all odd numbers from the index that I've generated earlier. These are the even numbers. Even numbers are required for cos function, odd numbers are required for the sine function. Last is the alternating sign. So I call this alternating sign, and this is quite simple. We are just going to take this in, we're just going to take negative sign, and we are going to raise it to the power of the index itself. And for even indexes, this will become positive number, and for odd indexes, this will become a negative number. And that's how we're going to alternate between signs. Alternating sign series, and this will be alt sign. So as you can see now, our signs are alternating, and we can now create these alternating even and alternating odd series just by multiplying these two series together. For example, let's say even alternate sine series is nothing but we take even series and we multiply it by the alternating sine series. So there we are. Now here this is the even series and with alternating signs. So in this manner we can create a Taylor series expansion. Before we forget, let me just remind you what we are trying to do here. We are trying to generate this Taylor series expansion of cos. What we have done so far is that we have been able to generate these even numbers and these alternating signs, and finally we have to sum them up together. And we have also been successful in generating odd numbers and odd factorials, and with alternating signs, and we'll make use of this. So we'll start with the cosine function. So we have to first decide as to how many number of points we want, how many number of terms we want. For example, in this, there are 4 terms, 4 Taylor series terms. It continues till infinity. So you have to decide how many number of terms that you want to include. So let's call that n terms. And in our case, let's say we want 20 such terms to be included. Now I will generate the x-axis, essentially this x part of it, which is going to go here. And I'm going to generate this x as a number which starts from, say, 0, and it goes to 2 pi in, let's say, 100 steps. So these are the various x values covering from 0 degree to 2 pi, that is complete 360 degree in 100 steps. And I'm going to store some array to save the output of the series of the entire code. So let me just say I'm going to save my cos signal in a placeholder called cos x, which is an array of all zeros. And how long should this array be? This is as many number of x points that we have. So we will save this, we'll initialize this array, and later on save our cos values in this particular array. So now we are going to loop over almost 20 times to calculate the Taylor series function. So before we would do that, firstly we have to loop over all the x's, that is all the values of 100 values of x which are there on x-axis, and then for each x value we have to compute the Taylor series. So let's start. For j in range the length of x, that means I'm looping over this entire series here for all the x's. So this is the outer loop, and I will save the result of my Taylor series expansion for each x in a temporary variable called result. And now I'm going to compute. Now I'm going to loop over all the terms of the Taylor series, 21 of them. So this is a loop of 100 for all the x's, and this is going to be a loop of 20 because of number of Taylor series terms that we have included for each x value. So now this will be n terms, number of terms. So we will do this thing in 3 parts. What we will do first is that we are going to generate the coefficient. For example, if you see this term, 1 by 4 factorial is the coefficient of x raised to the power 4. So we'll extract the coefficient parts first, and then we are going to multiply with the x terms, and then accumulate this entire series, sum it up together to generate the cos function for one particular x value, and then we loop it over for all the x values. So over to Python, and so let's first derive the coefficient first. So we know firstly that we need alternating signs, and how we can get alternating signs is plain and simple. We are going to take this and index it. So alternating signs have been taken care of. Now we have to take care of the factorial part of it. So factorial is in the denominator, so we go in the denominator. All factorials are even, so we know how even series is generated. That is just multiply the index by 2, and then take factorial of it. So I'm going to call numpy library for calculating the factorial, and this line of code has basically implemented the alternating sign and the denominator part. Now we're going to implement the x part of it. So let's call it x term, and x is raised to the power of even powers. So we are going to just use the same principle. We're just going to raise it to the even series, and then once we have calculated for all the 21 Taylor series terms, we have to do summation. So how we are going to do it is, we had stored this, we had initialized this temporary variable, we are going to use this. So result is equal to result plus coefficient multiplied by the x term. So this is how we are going to do this. And in Python, this operation can also be done very efficiently by just writing plus here, and it means exactly the same thing. So once I have done Taylor series calculation for one particular x, then I move on to the next x value. So before going there, I need to save this, otherwise it'll get overwritten. So I will, if you remember, I had initialized this array cos x. So I'm going to use this empty array. So I'm in the jth index. My x are looping over j, and my Taylor series is looping over I. So I'm going to save the result in my cos x array, and we are done. So we have implemented this whole formula for multiple x's. So let's see how this whole thing works. So we can do a quick plot, plt.plot, between all the x values and all the outputs or the y values. Y function here is cos x, and I have just enabled some settings, general settings. So we have an error. Oh, so we have an error, and the error has come because we have large number of x values, and here we have not specified which x value we are talking about. So actually we are talking about the jth x value. So this should set the code right, and let's see. We still have a problem, and that is because of this extra. So here we are. We have been able to successfully generate cos wave. We have x-axis going from 0 to 2 pi as seen here, and we have saved our signal in cos, and this is how it looks. So indeed this Taylor series is expansion of cos is working, and we'll now go over and build the sine series. So now we'll do the Taylor series expansion of sine. The code remains just the same. If you remember, we are now required to shift from even powers to odd powers and odd factorials, and the alternating sign remains the same. So this is what we're going to change. The rest of the code remains the same. So we have the same number of Taylor series terms. We have the same xx's. And now instead of calling initializing cos x, I've initialized an array called sine x, where I'm going to save all my sine values. I'm going to loop over all the x's, that is all values of x's between 0 to 2 pi. And then for each x, I'm going to compute the Taylor series. So here the coefficients are going to be slightly different because we're talking about sine. So in sine, we have to take care of the odd parts. So this is how the odd series will get generated. And firstly, we have to have same alternating signs as we saw earlier. So this is raised to the power I and divided by the factorial of the odd power. So this is what it is. This is the odd. And then we have to calculate the x term, which is raised to the power odd. So we are going to again take the jth k and raise it to the odd power, and we know what is the odd power. This is what is the odd power, so we're just going to copy it, and then we are going to save it in the result, accumulate it in the result variable, which is coefficient into x term, and then this result gets saved in this array that I had initialized on top, and then change the x, move over to the next x, and repeat this whole process again. So let's plot this sine x against x, and this should be sine here. So let's see how it looks. So we have to restart our kernel, and let's try once more. So there we are. So now you see that from 0 to 2 pi, we have been able to successfully generate the sine series from the Taylor series expansion using this logic. So far we saw the static plots of Taylor series. In this section we are just going to animate the whole thing. So this is for cosine animation. The function remains just the same. The coefficient is even number with even factorial, and the x terms are again raised to the power even. And this time we are just setting up the animation. The rest of the code is only to set up the animation. So let's just play and see how it looks. So you can now see how this entire cos series is getting built up using the Taylor series. So this is from 6 pi plus minus both the sides. So minus 6 pi to plus 6 pi. I'm going to stop this, and the next is sine animation. We have used exactly the same logic as we did earlier for the static plots, and the rest of the code is only to set up the animation. Let's play this too. So here you can see how the sine wave is getting generated using Taylor series expansion. And lastly, we will see both of them together. I'm going to switch off this plot, and now I'm going to use both the sine and the cos expansion for the Taylor series and plot them together. So this is how it looks. So hope you have found this tutorial interesting. Taylor series is a very important mathematical concept and used in multiple engineering and technology applications. Thank you so much.